My name is Sofia Miyazova. I'm taking over David's role as host for the VKC this season. David is finishing his thesis, and ahead of him is busy with finishing his thesis, so we wish him a smooth home stretch.
Thanks.
Yep. Hopefully next time we'll be congratulating you on finishing. A few words for Barbara. Yep. From Barbara. Yep. Okay.
I hope you're keeping your eye on the 12 VKC, but it's really beginning to take shape. It's only 10 months to the opening of registration. We've put a lot of effort since August in updating the website, so there's now a lot of details about the scientific themes and field trips. So Jennifer Pell is here, she's running field trip 2, short courses. Helen Gutter and I are running short courses. There's a lot more information on the website. If you haven't got your own flyers, or on the side here are business cards, flyers, and vinyl posters. So please take it for yourselves, and please take some to promote the conference wherever you go and whoever you talk to. And one important point is there is limited accommodation in Yellowknife. The 12 IKC have selected 12 hotels and negotiated preferred rates. All the booking links are now open. If you go to the website, you'll find the details. And I strongly recommend that you book your rooms now, because you're going to compete with the tourists when it comes to the time. And all you have to do, I believe, is give your credit card as a deposit, and the cancellation is not onerous. So please book your accommodation so you don't miss out. And I'm here if you have any other questions. Thanks.
First things first, we heartedly thank SRK Consulting, who continue to be our staunch supporters of this event, fusing academia and industry together. So our guest speaker today is Dr. Janine Kavanagh, who is based at the University of Liverpool, United Kingdom. She is a senior lecturer there and has been at the university for 7 years. Janine is a volcanologist and specializes in understanding the development and evolution of volcanic plumbing systems. Janine did her PhD at Bristol University, studying the ascent and emplacement of Kimberlite magmas. And obviously today's talk, which is the dynamics of Kimberlite magma intrusions, the role of dykes, is only a part of that large study. I'd like to remind that Janine will talk for 45 minutes, and thereafter a Q&A session will follow. So tighten your seatbelts for an interesting and exciting Kimberlite ride to the surface. And last but not least, I'd like to remind that we continue with our tradition of finishing up the VKC evenings at the Lennox Pub, where we will head after the talk. So, Janine, the floor is yours.
Okay, so hi everybody. Thank you for the introduction, and many thanks for the invitation to speak today. It's a real privilege to talk to you about some of the work we've been doing at Liverpool over the past few years, and in particular about dike propagation, and it would be interesting to have some discussion with you about the role of dikes in relation to Kimberlite magma ascent. So I just thought I'd start off by putting some fundamental kind of principles of what we're looking at here. So dikes are magma-filled fractures that are discordant, so they're cutting across the stratigraphic layers. There's some really nice examples here in a Shiprock dike in New Mexico. And what's particularly impressive about this dike is the way that the material is much more resistant to weathering than the surroundings, and so we can start to get a glimpse of the 3D geometry of this large sheet-like body. And so you can also see it here, and it's connected to this sort of volcanic pipe there. And basically these magma-filled sheets are often connected to some kind of volcanic plumbing system, which may then go on to feed an eruption. So the dikes are a major mechanism of transport structure for magma through the crust. But because they are sheet-like bodies, so they have this length to thickness aspect ratio about 1,000 to 1, that ratio is also sort of valid for kimberlite dikes. We idealise them as thin sheets which have an intruded the crust which has deformed elastically. But what's really important and is sometimes underestimated is the coupling process between the way that the magma flows and the way that the host rock deforms to accommodate the intrusion of magma. And that's something that I've been working on quite a lot in the past few years. So dikes are, there are basically all magma compositions that have erupted at the surface. We also have an equivalent dike intrusive breathing path in the system. And so dikes are important because they are basically the direct feeder of an eruption. So this is the Nakajima volcano in Japan, where you can see a basaltic dike just cut all the way through the edifice there and went on to feed a small scoria cone eruption at the surface. So you can see that the dike connects directly to the erupted products. But sometimes those dikes stall before they get to the surface. Not all dikes erupt. And it's actually estimated that about 80% of dikes never reach the surface. And this is an example, a very famous example from Iceland, of a basaltic dike which is cut through these very nicely layered ash layers. And then there's a lava flow up here at the top. But basically the dike has just stopped within the ash and it didn't go up and feed into that lava flow. At least not at this point, what we can see anyway. But what's important really is that the dikes are the major transport structure for magma through the crust. And magma of different compositions may be part of a complicated dike sill network where magma is sort of stalling along the way, or in the case of maybe kimberlites, it's more of a direct transport from the source to the surface along these very thin magma-filled sheets. But sometimes those dikes come to the surface and they will directly feed like a fissure eruption, for example. So what does this mean in terms of a kimberlite volcano? So you all know this very classic diagram here. And basically the dikes are an integral part of the kimberlite volcano. You know that we have these sort of key structures of the diatreme, the crater, and importantly in the case of today's talk, the root zone, which feeds into the kimberlite volcano. And that root zone can be a network of dikes and sills. And I want to hopefully convince you today that understanding the dynamics of the feeder system of these dikes and sills and how that then transitions into the vent is a key part of understanding the whole kimberlite volcanic system. So how are dikes and sills studied? Well, there's a couple of different ways that we can study them. The first is through field studies, and that would be to sort of geological work of looking at fossil intrusions, so basically where erosion has exposed the solidified magma at depth, and then we can go directly there and map it out, we can take samples, do things like this. But there's also things like scaled analog experiments. So this is my PhD student Simon, for example, who's very happy with his analog experiment there of plaster intrusion, which has fed a lava flow there, which was something that he did in Prague a couple of summers ago. This is a gelatin experiment, so I'm going to be talking about those quite a lot in the next few slides. And then these are some fantastic field exposures of dikes in Tenerife, where you can see these fantastic sheets, many sheets next to each other, and also cutting through the host rock there. But the other method that we have to study dikes and sills is through geophysics and geodesy. So when magma is moving around now, around our planet, and as it does that, it breaks rock and releases seismic energy, which can be detected by seismometers. When it gets into the shallow environment, it also can deform the crust in a way that can be detected from the surface through things like satellites. So we can monitor the ground deformation to understand where magma is, how deep it is, what the volumes are that are moving around, things like that. So these three different methods, those are basically the information that we have. Those are our key observations about what dikes and sills are. But they are all limited in some way, the information that we have. So problems and questions. So problems that we have is that all of those observations that we have are indirect in some way. So in terms of the fossil magma bodies, everything is stopped, everything is solidified, nothing's moving anymore. And we also have limited exposure, so we often just see a two-dimensional cross-section through something which we know is a three-dimensional body. In the terms of magma moving right now and the geophysical information in the geodesy, we have to infer what's going on at depth. We can't directly see and detect that magma, so it's all indirect observations that we've got to work with. In the terms of Kimberlite in particular, the deposits that we have to look at are often altered, and so that has additional complications in trying to reconstruct dynamics from this now static body. And also another problem is that both the magma and the host rock deformation are important, and yet the coupling of those two very key physical phenomena is not simple to do in terms of models and things that we would like to try and understand. So questions that I'm hopefully going to try and go through with you today are: how do dikes propagate through the crust, and what's particular about kimberlites in terms of these particular dynamics? So I'll just start by sort of outlining the kind of theoretical framework of how we model dikes. As I showed you at the start, we idealise dikes as a planar sheet which is intruding an elastic material. This is just a cross-section through a schematic dike. So we've got our fluid-filled crack here, which is going into our host solid, which is an elastic material. And important here is that the intrusion time is short, so the processes that we're looking at are rapid, and the crust is therefore deforming in an elastic way. We've got key pressures that we need to think about, so those which are driving the magma propagation, driving the crack to grow, and those are things like the elastic pressure and the buoyancy pressure, but also the resistive forces which are stopping it from growing, and those are things like the fracture pressure, so basically the pressure required to grow the crack. If you don't overcome that, then you haven't got enough pressure to grow it, so the dike will stop. But also the viscosity of the magma. If it's very viscous, then it's not going to flow anywhere. So those are things that we need to think about in terms of pressure scales. And in terms of flow, we might also think about something like the Reynolds number. And so there are a couple of different models about which are suggested for how dikes grow. The common one, and the one that I tend to use in my research, is that dikes are hydraulic fractures. So they are fractures which are driven by a fluid which is applying a pressure, and that's why they're growing. But often when we look in the field, we'll see dikes not as a single sheet, but as a series on echelon segments. And one idea about why that happens is because it's to do with the way in which the crack is opening and the pressure and the stress conditions working at the tip. So in this hydraulic fracture model, if it's just mode 1 opening, which is just tensile opening, we just have a crack, a straight crack, which grows to the surface and just has that very nice straight fissure type expression at the surface. However, if you've got some kind of mixed mode loading, so some kind of shear which is developing, and that could be because the dike has gone into a different stress field, for example, and it will start to bend and respond to that new stress field, which is creating a shear, and so we could get the dike trajectory bending over. And the third mode is again a mixed mode, but this time we've got shear happening in the lateral sense, and so a single dike could transition into a series of fingers through that rotation which happens. A little bit like your hand being twisted and then your fingers kind of splitting like this. So we can get a series of on echelon dikes which actually connect at depth to a single sheet, but it's just that in that new environment it's twisted and broken up into those fingers. So this is basically models assuming elastic deformation of the crust. Something which is also discussed in literature is this viscous indenter model, and this is basically where the host rock is not deforming in an elastic way, it's deforming in a plastic way. And that is something which I think might be of interest to you when we discuss some of the field evidence and things like damage zones around the tips of dikes. So that's kind of like about the way in which the host rock is deforming, but as I told you, it's very important to think about what the magma is doing as well. And so there are different things we need to think about there as well. The first is that there is a model of basically a buoyant ascent of magma. So magma is generally buoyant as it ascends through the crust, so it's lower density, and that can be because it's exolving gas, for example. And if it's a buoyant ascent, then actually the overall cross-section of the shape of the dike will have a very characteristic teardrop to it. So it's very wide at the top, and then it pinches closed at the tail. But the flow of the fluid within that buoyant crack is kind of like recirculating inside here. Another model for the way in which the magma is flowing within the dike is that there is an external pressure, an external flux, which is basically pushing the fluid into the dike. So it's a remote pressure pushing it in. And so we get a very simple flow trajectory inside the dike. There's this third model as well, which I think is quite interesting because we often think about magmas just moving vertically. However, there's a lot of evidence which suggests that dikes can move sideways as well. So you can get what is called a bladed dike, where the dike is closed at the top and the bottom, and it's basically just moving in this direction. And that's a third type of dike. Finally, the thing to think about is this a passive or an active intrusion? So is the magma sort of passively filling space that is created due to tension, or is it actively pushing its way and creating new cracks and forcing its way through the crust towards the surface? So there are lots of things that we need to think about in terms of underlying models on how dikes propagate. And what we can do is we can go and test that in the laboratory and go and see what the evidence is like in the field and try and assess what happened really in the past. This buoyant dike ascent, I think, is particularly relevant for kimberlites because there's a lot of evidence which is suggesting that kimberlite is particularly volatile rich, so a lot of gas tends to be exolved during ascent. And dikes have been studied experimentally in the laboratory using scaled analogue materials. I'm going to talk about that a lot in the next few slides. But some of the first experiments were just simple ones like this done by Dike in 1990. And this is a gelatin solid. So gelatin is an elastic material when it's cold, which means that if you apply a pressure and you release it, then it has an elastic response and it comes back to where it was before, no permanent deformation. By injecting a very buoyant fluid, in this case an oil, we create a little dike down here, which then takes off, and it has this is the cross-section shape. You can see it's very, very thin and it's pinched here, and basically it just rises as a kind of blob-like shape, which is very thin in profile. There was also some work done in the early 2000s about the effect of having a lot of gas and in the tip of this fluid-filled crack. And that showed very nicely how if you have, for example, an air bubble and then a liquid below, this is the dike that would be created in that elastic material. This is looking in plan view like this, so not in cross-section, this is looking like inside the dike. And you can see that just the presence of the air bubble really narrows the width of the dike, and so that buoyant tip starts to dominate the behaviour and create the pathway which the fluid then fills afterwards. So we've got these nice experiments which are sort of demonstrating what the expected geometry of the dike will be in the 3D, and then we can start to look in the evidence in the field about how that geometry is actually expressed or not. So I'll just tell you now about some of the experiments that we've been doing at Liverpool. So in these experiments we use gelatin as our crustal material. We then inject into the base of that some dyed water. This is a clear perspex tank. It's 30 centimetres high, 40 centimetres square. This is a side view of the experiment, and then this is the top view. And on the outside of that tank, we put some polarizing sheets. So it's the same polarizing sheet type material that is used in lots of applications, and it's basically really helpful to use in gelatin because gelatin is photoelastic. So any stress that is induced in the gelatin, you can see it by a colour change by using the polarizing sheet. Then on the top of the tank we sprinkle some sand so that we can put a laser, project a laser sheet across the cross-section of the dike that we create. And basically we measure, a laser measures the distance from the laser to the surface of the gelatin over time. So we're able to track the surface deformation as the dike grows. So those experiments are initially hydrostatic, so there's no pre and post stress. So it's a very simple experiment, and there's a constant flux driving the fluid in to the base. So I'm just going to show you a couple of videos of one of these experiments. So they'll play simultaneously. So this is the view from the top, so this is the sand and this is the laser traverse. This is the polarized light view, and then this is the 90-degree view, just a normal artificial light. So hopefully, maybe you can just look at the polarized light one. You can see that the stress is around the tip of the dike is expressed through these very nice birefringence colours, making kind of bow tie pattern of stress distribution around the tip. And then in 90 degrees from that, we've got this very nice penny shape crack. So it's very, very thin in this direction. And then almost circular in that direction. And then when it reaches the surface, you get a very small fissure erupting at the surface under the bark flow. So what's quite interesting, even just from looking at this very simple experiment, is how the surface expression, so the actual fissure that is formed, is much narrower than the actual width of the dike at depth. And so that's something that maybe we don't always think about here in the field, about how the exposure that we've got is actually probably very small in comparison to the potential underlying system that's fed it. Okay, so we can start to analyse that data in a little bit more detail. So here I've plotted the dike dimension against time for 2 experiments. The filled circles are the length and the open circles are the width. And then down here, I've got the velocity against time. And basically, from this data, we can start to identify different stages of dike growth. The first is this stage 1, which produces this nice small penny shape. And you can see that in the data here because the length and the width of the dike are identical. So it's growing in this dimension at the same rate as it's growing in that direction, so we get a nice circle. You can also see in the velocity that it's the tip velocity is decelerating. So there's initial growth, and then it's sort of slowing down. And that's because the penny shape is being established. It's thickening rather than growing in length and width. Then we've got this stage 2, though, which again, you can see that the length and the width of the dike are on top of each other. So we've still got that nice round penny shape. But this time the velocity is stable, so there's a constant velocity as the dike is growing. And then the third stage is this bit over here, which we can notice in the velocity plot is this acceleration towards the surface. And that's where the dike is approaching the surface, it feels that it's towards the surface and accelerates towards it. So we can see that very nicely here. We also see it in the data because the length of the dike becomes larger than the width, and so it's sort of becoming stretched. As it's doing that. Something else I wanted to point out here is basically how reproducible the experiments are. So those are 2 different experiments, and the length and width and the velocity change over time is basically identical. So we have spent a long time characterising the materials and how they are sensitive to time and temperature. So we're able to basically run the same experiment again and again, because every time we run an experiment, the gelatin is destroyed, so we can't use it again. So we need to make a new experiment. But when we do that, we know that we've got very good control on being able to basically have the same experiment run again. And that's really helpful when we're using different imaging techniques which can't be used at the same time, but we want to try and understand what's going on in our experiment. So that fact that we can run the same experiments again meant that I can now show you some other experimental techniques that we've been using to understand Dike dynamics. This one, we use passive tracer particles which are suspended in the gelatin, and we illuminate the tank with a very high intensity laser sheet. So this is again the side view. So we've got our tiny passive tracer particles in the jelly, our vertical sheet which is then cutting through the centre line of the dike which grows. I should say that during these experiments you can't really see anything at all. We have to be behind the safety screen, and we have to wear these very silly looking glasses which basically block out all the light. So we sort of press the button, hope it works, and then find out about half an hour later if it did or not. So there's a little bit of element of risk involved, but we found some really interesting stuff. And basically we found that interesting stuff by doing this technique called digital image correlation, which is something which is used in engineering almost as a standard practice, but it's something which is quite new to geosciences and analogue experimentation. And what it does is it's a pattern matching technique. So rather than tracking individual particles and where they go, from two different time steps of an experiment, an algorithm compares the pattern of particles in one stage compared to the other. And from that, you can then calculate the displacement, so how particles move, and then from that, the strain. So either an incremental strain, so like capsules of time of what the strain is doing, or a finite strain, so like a total strain, so how the total strain is evolving during the experiment. So then this is going to show you one of the experiments, and basically what you're going to see is Dike cutting up through this gelatin slab. This is the start of the experiment, so the laser is basically fluorescing all of these passive tracer particles which are in the jelly. Okay, so hopefully you can see the little dike growing there. You can see it's very thin, it's probably 2 or 3 millimeters thick. It's slightly inclined, and it has, you can start to see the tip there, and then it erupts and it's gone. So, and actually you wouldn't even know it's there, because it's an elastic material. When you've erupted, you've released the pressure, so everything just closes back up. Yeah. So there's some, I'll just show you that again, because what you hopefully can also see is how the shape of the dike changes. Just by eye you can see those particles moving, but if you start to look down here, can you notice how this is now becoming very thin and pinched? This part is open, and then the whole thing is just gone. So this technique of shining that high intensity laser through the tank enables us to get a really nice cross section of the shape of the dike. And that's basically the kind of data that we have in the field, because we often just see a cross section. We either see a vertical cross section of the dike, or we see just a horizontal plane. So it's kind of like directly comparable to that. But using that digital image correlation technique, we can then map out what the incremental strain looks like during an experiment. That's what I'm going to show you here. So there's little simulations. Basically, they've just shown you that you've got this sort of strain intensification at the tip. So that's where the material is being broken and opening to accommodate the dike. You also get, this is the vertical strain, and you can start to see some displacement at the surface as the dike approaches. And this is the shear, which is particularly interesting to seismologists. Again. So something which happens, which you can see in these images, is how as the dike grows, suddenly there starts to get a little bit of blue down here. And And in particular, as it erupts, then there's that blue patch, and that's basically because the gelatin is coming together and closing and then zipping closed as the dike erupts. So that was about how the solid deforms, but also we can have a look at what's going on inside the dike. So we use the same technique of shining the laser, but this time we've oriented the dike so it's in the laser plane directly. So you can see here that that's the view from above. It's a very thin laser sheet, it's just about 2 millimeters thick, something like that. But this time our passive tracer particles are inside the fluid that we inject. And we do this thing called particle image velocimetry, which is the same, pretty much the same technique as what I described before, but rather than getting displacements and strains, we get velocities. We get a velocity map. And this is what you see inside the growing dike. So basically, everything is black in the surroundings because there's no particles there. We create the dike, and just by eye, you can see there's some interesting structures inside that. Very simple penny-shaped crack. And I'll just show you that again. So hopefully early on you can see there's some sort of like vortices developing, and we start to get this sort of rapid channel in the middle. The particles at the edges are coming down, and then as the dike approaches the surface and erupts, then all the particles coming out because the fluid has been expelled out of the top of the dike. I have to tell you that I was quite surprised when I first saw that experiment, and I was like, wow, this is so cool. Because we've been doing the experiments for, well, I've been doing them for like 15 years, and I'd never seen that kind of interesting circulation pattern inside there before. But I'm working with an engineer, and he was like, yeah, obviously it's going to do that. So that really, I was like, oh God. And so it really basically identified to me how we need to talk to each other a little bit more across disciplines, because geologists really don't know that that's going on inside dikes, for example. But anyway, that was interesting. So then actually we can then look at the flow map within that dike using that technique called particle image velocimetry. So what you're going to see is basically a colour map where the bright red and yellow, those are like fast areas, and then blue and pale blue and white is like very slow or not moving at all. And then the black arrows are showing you the direction of flow. So this is the velocity. Basically, you can see that very nice channel or jet-like feature in the middle of the dike. It's got this sort of blue around the edge, and there's a kind of flow of fluid down at the margins of the growing dike. And I'll show you it again. But you can kind of see how there's sort of rapid jet, and then there are kind of like dead regions which develop where it's very low or very slow or not even moving at all regions of fluid. But then the kind of recirculation of material around the margins. And that's quite interesting because basically it's representing this competition between the fluid being driven into the dike and the dike being able to grow because it's got to crack the gelatin. And there's that kind of competition going on between fluid flow and host rock deformation. But from that experiment, which is just water injected into jelly, we start to identify some really nice, interesting structures. So this sort of core region of this jet, and then these sort of vortices, fluid recirculation around the margins, and then the creeping flow at the front as the crack is growing. But something you probably noticed as well is how that jet becomes a bit unstable towards the surface, and that's this sort of flow instability. And that's something that's quite interesting, and I've been trying to understand how that happens. But just to kind of bring it together, I just want to sort of show you how the information we've got about the geometry and then the flow and then the host rock deformation, they're all really linked. So for example, in this early stage of dike growth, this sort of stage around here, we've got this basically just a sort of penny-shaped crack growing, and the flow of fluid inside is kind of recirculating around as that small penny is first growing. And then we've got this second stage of the fluid starting to develop that jet-like structure. And then this again, this is when the crack is still penny shaped, so it's still nice and circular. But then you get this sort of effect of the stress being concentrated at the tip. And then there's that pre-eruption unsteady moment which happens where the jet starts to become unsteady. And you start to detect the dike at the surface, and it starts to become more elongate. And we start to see the deflection here, and this sort of pinching starts to happen at the base of the dike. And then the final stage is the actual eruption, where all of the fluid comes out of that very small fissure at the surface. And that's where we start to see this zipping and close of the dike from depth. So hopefully that demonstrates how we need to think about the way in which the host rock deforms, the way in which the magma flows, and the way in which the geometry of the dike is basically reflecting all of those different kinds of processes, and how that acceleration towards the surface was basically, that was the point where the dike became dominated by buoyant ascent, and that sort of was reflected in that very nice teardrop shape developing in the dike profile. Okay, so just in the sort of last part of the talk, I want to think more with you about what this means for kimberlite magmas in particular. And so there are kimberlite magmas, there's a lot of unknowns, as you know, but my understanding is that the composition is, of a kimberlite magma is probably somewhere between basalt and a carbonatite, and so something like that. And so these kind of pictures, these kind of physical processes, physical properties might be relevant to kimberlite. So we're thinking low viscosity melts, high gas content of water and CO2, could be very explosive, but also evidence of diffusive eruptions. And then some of the ideas that have been talked about in the past few years about this sort of proto-kimberlite, basically its composition and its physical properties changing during ascent. But we think probably that kimberlite is somewhere around here in terms of melt viscosity, so sort of like motor oil or very runny basically. And there's some nice evidence that this is probably the case. So for example, the fact that you've got really thin melt coatings around lithic fragments, or that's basically evidence that you've got a low viscosity liquid. And also this is a kimberlite dike in Swartruggens line, and there's a really, really thin dike just there, and you can't basically get a dike like that happening unless you've got a very low viscosity liquid. So there is some understanding, I think, about what the physical properties of kimberlite melt and magma really were. But I wanted to show you some of the field evidence that I worked on in my PhD about some of the evidence that we got from the field about how the host rock is deformed and what that means in terms of eruptions. So I'm going to talk about two case studies that I worked on. The first is Venetia in South Africa, and then the second is Helm. And so these are two different systems, but they're basically telling us about two different parts of the system. First being in the dietary classes, and the second being kind of in the root zone. So in Venetia mine, lots of people will know a lot about this. It's about 14 bodies intruded about 590 million years ago, intruded into a Proterozoic metamorphic basement, and it's got lithic breccias in the K1 and K2 in particular. And just a typical volcaniclastic deposit, so we've got a very lithic class being very well mixed, olivine crystals. And the work that was done in Bristol at that time sort of advocated this fluidization of material in the dietary, causing that very well mixed material to be coming all jumbled up all together, and some interesting unfluidized regions of strata developing, but sort of key being this large gas flux mixing all the material together. But when we were there and working particularly with Richard Brown, we sort of noticed how there was this interesting spectrum of shapes of lithic fragments that were in the convection pipe, sort of going from very round to very angular. And in particular, we noticed some of these clasts had this sort of concentric rines or kind of like, looked like onion skin type weathering that you might see at the surface, but this is within the dietary deposit itself. And sometimes within the deposit you find just those detached little rinds of those blocks as well, which is suggesting that kind of peeling and that rounding on those clasts. So it's not the only way that you get rounding in kimberlite, obviously, but one of the ways might be through this kind of spalling off of little chips. And so we found these extremely well-rounded sporoidal lithic clasts, and they seem to be about 5 to 15% of the lithic clast population. And they were basically characterised by these sort of fresh cores surrounded by concentric shells. And some of those platy clasts then became broken up and incorporated into the richer matrix. So those were some observations that Richie made in Venetia when we were discussing some of the ideas about how they might have formed. And then I started working at Helen Mine, which is looking at the some dykes, which presumably would have fed some kind of pipe at the surface. At Helen, basically there are 3 dykes. 2 of them are kimberlitic, one is a lamprifier. They intruded at the end of the Jurassic. The whole array is 7 kilometres in length. And these are a series of anastomosing on echelon segments. You can see all the different segments here in plan view. And each of those segments are several hundreds of metres long. And this is a cross-section through the area. So the red is the excavation, and then the other colours in the background, that's the stratigraphy. And something that we sort of noticed in this schematic cross-section of the dikes is how there is this pinching in geometry which happens in the dike at that kind of interface. It seemed to happen at this interesting place where the host rock is a quartzite here, so a very strong material, and you've got a shale layer, so a very weak material. And so that reminded us of some analogue experiments we'd done a few years previously, where we were using gelatin, and we'd basically injected water into the gelatin and created a dike which cut through the layers. But at the interface between 2 layers which had very different mechanical properties, we got kind of pinching, so that kind of pinching. And so we wondered if potentially the dike moving up through those mechanically different rock layers had been partly responsible for that kind of pinching in the width of the dike. So then I mapped out those, I took the data from the mine, which is a really exceptional data set of the 3D geometry of kimberlite dike, actually. We don't have those kind of data sets for any other magma composition because nobody else is mining out dikes in that way. So this is a map of dike thickness for 2 of those segments. One's called Edward and one's called John. And so it's several hundred metres in width, and then the stratigraphy over several hundred metres of depth. And this is the stratigraphy here, so you've got dolerite and the shale layer and then quartzite. And the dike thickness is coloured here. So basically we've got some elongate channels, elongate regions where the dike is thick, and then areas next to that where it's thin. So there's a thick region here, and there's a thick region up here. And when we first looked at this data, I was basically noticed that these thin regions seem to be like at the terminations of the dike segments. That's where it was particularly thin. And then mapping out the geometries and some of what the host rock looked like in those areas, we found that the material, so where the dikes were very thin, the host rock was very broken and brecciated and deformed. So here is several closely spaced dike parallel fractures in the host rock next to the dike. So we think this is the damage zone, so this is rock which has been broken because of the presence of the dike. Don't see that kind of damage away from the magma.
And then also this interesting kind of structures of magma and host rock deformation, which I'm going to talk to you about in more detail later. So lots of interesting structures. So here's a Kimberlite dike, and there are some entrained blocks which are held within the dike. We've also got these asymptotic fractures in the margin of the dike. So this is the dolerite, this is the Kimberlite. So we can see these kind of fractures. We've also got some labels. And then, so this interesting spheroidal blocks, which are the dolerite host material, but have got these like rounded shape to them. Then also places where the host rock is very brecciated, and the kimberlite is kind of blob-like in its structure. So we've got thin sheet-like kimberlite, and then we've got blob-like kimberlite as well. So that was interesting. They had these different kind of structures, but the basically thinking about how the host rock is being damaged before the magma is coming in. And so this was a really nice exposure to sort of go through some of that temporal evolution of how the rock gets deformed. So just to get your eye in here, this is the kimberlite, so it's like a few centimeters thick stringers. It's what we call a really thin dike, and you can see it sort of cutting through here. We've also then got these rounded blocks within the dolerite host rock. And those blocks have got a fresh core and then these concentric onion skin shells around them. But those rounded blocks, they seem to be bound by joints or faults, so you can see those kind of things there. And so putting that all together, basically we can get a time sequence of host rock deformation and magma intrusion, where we've got these fractures which are created first, and then within those fractures there are gases which will have, from the magma exhaled at depth, which have streamed through there and then altered the rock, spheroidally weathering it like at depth in situ, probably 1 kilometre, 2 kilometres depth, something like that. And then the last thing to happen is that the magma comes in and it kind of wraps around some of those preconditioned blocks. And as we saw in other places, then can even incorporate some of those blocks and carry it up in the magma. So from those two case studies, basically we thought we had evidence to suggest that we had some preconditioning of the host rock at depth, which was associated with the dike propagation. Then during ascent, that material can then get brought up and out and incorporated into the diatreme as part of the cargo there. So there was those interesting structures that we saw in the field, and then going back to this sort of thickness map, I'm wondering now if some of these vertical thick channels might also be related to some of those jet-like features that I've now started to see in my experiments. We've got very rapidly rising and probably eroding channels within, or jet-like linear features within the actual dike itself. And so the host rock deformation, but also the way that the fluid flows, being responsible for creating that final geometry. And the thing about the kimberlite in particular is that it has this low viscosity, it has a high volatile content, buoyant ascent, host rock preconditioning through damage, brecciation, alteration, and then host rock assimilation. And in a recent paper that we've just had accepted with Kelly and Steve, we kind of brought all this information together into a schematic model. So to sort of try and understand better how the Kimberlite dike and the role of the Kimberlite dike and its ascent through its way to the surface impacts what we then are able to see in the shallow crust and in the erupted deposits. So at depth, the cross-section of the dike will probably look something like this. It's going to be a teardrop shape because it's got so much volatiles which have been exolved, so it's going to have a very buoyant tip. So it's going to be more of a teardrop shaped profile, pinching closed at the base here, and a gas-rich pocket at the top. And then in the plan view, we'd probably expect to see something like this, where we have a gas-filled tip, which is buoyant and then rocketing up, and therefore you've got a narrower tip here compared to at depth. But within the fluid, you've got a sort of magma jet, which is high velocity, carrying that some of that material which is broken off from the host rock and mixing it up and round. And then using some of the ideas from like Tom Kelly's work about how you could have turbulent mixing and attrition happening in that buoyant tip, and how basically the damaged material, the damaged host rock is incorporated physically and chemically into the magma as it intrudes. And as that dike then comes to the surface, it will potentially precondition the country rock and start to get volatiles streaming through, that kind of alteration. And then the new magma which comes in is preferentially going to go through that material which is very weak. And so those preconditioned areas are going to be the focus of places where you would get your volcanic vent forming. Okay, so some implications and conclusions. Hopefully I convinced you that Kimberlite dikes have some interesting dynamics with important consequences. Some of those are going to be important for things like diamond transport and preservation. But it's the low viscosity, buoyant and likely turbulent ascent which are key to understand the dynamics of the dike. The host rock is mechanically damaged and chemically altered by the growing dike because the magma is ascending, it's dissolving volatiles in this volatile rich tip which develops and then could potentially ascend ahead of the magma-filled crack. You've got that teardrop shape geometry, and that teardrop is actually kind of enhancing the damage which the host rock undergoes. That damaged material is then physically and chemically incorporated into the magma, and that magma jet, that high velocity jet within the dike, is transporting and potentially recirculating that cargo within the dike as it grows. And hopefully I've convinced you that understanding dike dynamics is really fundamental to understanding the Kimberlite volcanic system. Thanks.
So if anybody has any questions, we have time for that.
In the gelatin experiments, it looks like you already know what the orientation of the dike is going to be. How does the dike fracture begin in that experiment?
So we have no predefined stress in our model. So in order to control the direction of the dike, which we need to do to make sure that we get to image it in the way that we need to image it, we make a pre-cut. So we make a small cut in the direction that we want the dike to grow. We then insert the needle into that, and basically it grows that existing crack in the direction that we want. We also have a tapered needle, which helps to form the dike in the direction that we want it to go. If it didn't make a pre-crack, then it would be in a random orientation, and sometimes you get like multiple dikes growing. And so, although that's pretty, it's sort of inconvenient, and so we have to have that little starting crack to get the whole thing going.
Yeah, I had the same question. If you did not make that crack, what prevents the experiment from creating a plume?
So,
a radially symmetric plume?
Yeah, because it's an elastic material, it cracks, and so it's not plastically deforming. And so, even though you wouldn't make that pre-crack, you would get basically like several cracks growing. But very quickly, one of those cracks becomes dominant. And that's because the longer the crack, the lower the pressure that's required to grow it. And so you may start off with a couple of dikes, let's say, but then actually one will become dominant, and then that one will grow, the others will just stall. Will just be in the wrong orientation for us.
Have you ever thought of any possible ways to put stress on the gelatin before the dike starts so you can see what that effect would be?
Yeah, so these experiments are extremely versatile. There's lots of things that you can do. You can make layers of different mechanical properties, and you can apply different stress fields. So a couple of different stress fields are of particular interest in volcanology. One is an extensional stress field. And so what we do there is that we basically put these metal plates in the tank before we pour the gelatin in. And then we pour the gelatin in, let it solidify, and then we circulate hot water through those plates. So we melt the edge of the gelatin, take the plates out, and then fill those voids with water. And so you've got like a free boundary there on the jelly, and then you weigh it down, and so it expands, create an extensional stress field. Or you can do the opposite, which is to have those plates in and then put more plates in and create a compressive stress field. Or you can have, so those are like regional stress fields that might be of interest. But you can have local stress fields as well. So, for example, having like a volcanic edifice on the top, that's been done, or an unloaded stress field like a caldera, for example. And so, yeah, you can definitely, the stress is really important. And,
what about faults?
Yeah, sorry?
Faults. What about faults?
Yep, faults, so you can cut your jelly and have a look at the interaction of the dikes with those faults. And what seems to happen is that so if you have a couple of faults and you put your dike in the middle, they basically act like a stress diffuser almost. So the stress of the dike itself, because it's pressurized, is only constrained between those faults, doesn't transfer across into the other boundary, at least in the gelatin experiments anyway. And we've been doing some experiments recently where we tried to get sealed faults, so hot knives kind of cutting and then partially sealing, and maybe also cut layers and then another intact layer on top, so like buried faults, things like that. So lots of them.
Do I understand correctly that the ground preparation, tectonic ground preparation, is not as important as the magma composition for the dike placement? The final sort of.
Interesting. I think both are important. So basically, you need your magma to be able to move. So that means it needs to be certain viscosity and certain pressures involved. So if it's very crystal rich, for example, or if it's very high in silica, then you need much larger pressures in order to get it to move. But also if you've got tectonic stress fields where it's very easy for a magma to come into that area, they can almost do it passively, filling in the space, then you don't need so much pressure, so you can potentially get other magmas coming in.
So for kimberlitic magmas,
Yeah.
I guess the composition would be of prime importance rather than ground preparation.
So I think that, well, my understanding for kimberlites is, based on some of the work that Wayne did, that sort of these sort of very lithospheric scale fractures seem to be channeling the magma up, and so they are kind of like a preferential place where magma could go. I think it's probably a combination of having these faults which are very easy to intrude, and then having magma which is very buoyant and wants to come up. So it's basically both things.
Any more questions from the audience?
For this picture, if we take your understanding of dike propagation, magma transport and dikes, have you thoughts on Hawaii where you get these very prolonged eruptions that are fissure-fed?
Yeah.
So what's the dike model that's feeding those long-term eruptions?
So in Hawaii, the dikes are mostly natural dikes, so they're going, there'll be some vertical component, but actually they're mostly going sideways as blade-like features. And then that's basically like an open channel through which magma can go easily flowing. Somewhere like Hawaii, where you've got almost a continuous production of magma, it's just a very easy way to get it all out. And last year, there was some really nice things going on in terms of that fissure eruption, where the early stage, the first magmas that came out were quite viscous, producing like RR flows, and there was magma which had been around in the system since the 1950s, and then this very hot, fluid, young magma from the lava lake came pouring out after, and that was the one that then travelled very far, very long distances. But I think that the something which is maybe not very well understood, but could be quite important, is these jet-like features in the Dike. Because basically those are going to be channels where it's very hot, and it kind of focuses the flow. And so even though your Dike could be quite big, if you're focusing all of your magma through a small channel, and like in a lava flow, it sort of insulates it, enables it to travel further for longer. That might be going on in dikes as well.
Also, you have the thought that the Fisher expression is a small linear distance relative to the width of the dike.
Yeah, even more so.
So if we look below this, is the lava lake fed by Fisher? Like if that's the source of the magma coming in and then it's spreading laterally.
Yeah, I believe so. Yeah, yeah. So, so in terms of the lateral dike, I guess the seismicity will often tell us where the top of the dike is. It gets a bit fuzzy at depth. I don't really know how deep it goes. But the idea is that it's closed at the base and that it's lateral in that direction, and basically just a little bit. And this is actually Iceland in 2014. But same thing.
I'd say probably clarification. It wasn't so much fractures we looked at, but stress. So one of the ideas is that in low mean stress areas where you where you can hide your toric stresses, but there's low confinement, it's more likely to get through. Do you, in any of your models, you said you simulate those stress? You can simulate stress. Would the dike naturally move to a low mean stress area?
Yeah, it does definitely.
Yeah.
So I showed it a little bit in the slide I had about how we study dikes. And I had a gelatin picture, gelatin experiment there with polarized light, and that was 2 dikes on there.
Right.
And so the thing is that dikes will also create their own stress field, and so they will interact with each other. And so definitely the stress, whether it's whatever is causing the perturbation and stress, could be a local thing, could be a regional thing. That's very much going to affect the trajectory of the dike, and also which is going to be more dominant. So yeah, it's low stress areas. Very important for a channel with lots of fluid.
Okay. Thank you very much for the interesting talk. Made it to the surface without explosion. I'd like to remind that Janine is with us for 2 more days, so she will be giving talks tomorrow and on Friday at UBC. Tomorrow's talk will be on modeling magma movement, and on Friday the talk will be dynamics of dike and seal emplacement insights from analog and field experiments. Although those who are interested are more than welcome to join the presentation tomorrow. Yeah, and I'd like to thank everyone for attending today. First opening talk, and especially given that the weather is not very nice. Also, please don't forget to pick up the flyers from the 12th International Kimberlite Conference. And we are heading to the Lennox pub right now, so everyone, again, welcome to join us to continue our socializing. Thank you.